star chart. That's another star chart. I think this star chart's cooler. Yeah, it is. We've got to go from calcium. That's 10. Oh, wait, where's my calcium? Calcium, here we go. Open up, full screen. The lights are popping. So again, this is where I'm going to show the trends in this table, this chart of the nuclides. So we'll leave this together. If you remember how the gap between oxygen and the calcium was, look at what happens again here. Between the calcium's doubly magic numbers, you got this vanadium, 100% isotope, an alpha particle up, 100% isotope, alpha particle up, 100% isotope. These are trends that aren't shown in the table. And this is why I'm coming up with new ways of doing this. So let's zoom in a little bit and see what these exactly are. Zoom in a little more here. We've got vanadium. Vanadium 51 mass, odd number, 23 protons. Even number neutrons, odd number protons. 100% of the vanadium atoms that you find, there's only one isotope, and that's going to have a mass of 51. Exactly an alpha particle up, your manganese. 25 protons, odd number, 55 mass, odd number. Exactly an alpha particle up, cobalt. Remember, iron was what they say is the biggest element that's made pre-supernova in stars. Well, it's all three in a row, really, if you look. It's iron, cobalt, and nickel. But the cobalt, again, 100% of the isotopes that you find for cobalt, 27, it's got to have 27 protons. That makes it a cobalt atom. The only isotope you find will have 32 neutrons. What's that mass? 50. It's hard to read. Let's hone in on it here. That's as far as it goes. 59, I believe. But this, again, was something that I discovered. When you look at the alpha jumps, we'll call them, okay? In between the oxygen and the calcium, there were alpha jumps, fluorine, sodium, aluminum, potassium, phosphorus. These 100% isotope alpha jumps, alpha jump, but now look at chlorine. It splits. Instead of having 100% of one type of isotope, there's two predominant isotopes with a gap in between them. Now chlorine is going to have an odd number of protons. Can we hone in on this? It doesn't zoom in very good here. That's actually the later one. I guess we missed our chlorine jump. Okay, so here it's a copper, 29, odd number, 29. Even number neutrons, 29. Even number neutrons. The two predominant isotopes of copper that you find, I can't even read those myself. I don't know how you're going to read them. But anyway, another split. Gallium has a split. After gallium, what do we have? 100% of the isotopes of astatine, 33 protons, 42 neutrons, a mass of 75. All the astatine atoms that you find are going to be that isotope. Now, bromine does the same split here, huh? Now, bromine, if you remember, is in the same family as a chlorine. These are the trends. So I'm going to have to make a three-dimensional chart of the nuclides here to wrap it around so that the chlorine and the bromine line up. Chlorine was the first one to do the split. I guess I didn't have it here to show you, but bromine does that split. The copper did. And now look above that, 100% of the isotopes for rubidium. There's only one isotope. The only one you will find is going to have, has to have, see if we can hone in on this, huh? It's got to have 37 protons or it's not going to be a rubidium atom. After rubidium, 39 makes it a yttrium. 100% of the yttrium atoms you find are going to be an 89 mass. So if it's got 39 protons, it's got to have 50 neutrons. 48 even number neutrons. 37 gives you an 85. Now see, these are alpha particles apart. Is this just a coincidence? I find this fascinating. No one's ever explained it to me. I have a research degree in chemistry, minors in physics, biology, took a bunch of math, lots of music. Only took me 3 terms to get my diploma. Reagan, Bush, and Clinton. And 2 of those were doubles. So, 100% of the isotopes you find are these. We're going to back up here. Now, a good trivia question is, what element has the most isotopes? And what we're going to find is it's going to coincide with a magic number. Would you find that hard to believe? We kind of take that for granted now, huh? Let's zoom in on some of this here. Here's that split again. Silver does a split, 2 of the isotopes with a gap in between them. Got odd numbers protons, even number neutrons, odd number isotope. This even one in between there may exist, but the percentage of it is so small it's negligible. The splits, they're either 100% isotope or there's a split. So again, indium, 100% isotope. Odd number protons, even number neutrons, 100%. The point we're talking about here is tin. Most number of stable isotopes, you call it. So if you get a sample of tin, it's going to, nearly every sample could be different because there's a different abundance. What I'll do next is do a chart of the nuclides where each box is bigger for the isotopic abundance. I'm trying not to use these big words. Only took me 15 years to learn how to pronounce them. So the isotopic abundance of tin varies between these, but each box is pretty much the same size here. But how many different isotopes exist for tin? More than will fit on the screen. What do you think of that? And as we would expect, there's a magic number. Huh? What's the atomic mass? Atomic mass doesn't matter. The atomic number for tin, number of protons, 50. So you remember our 100% isotopes were all odd-numbered protons. Now we get to the next magic number, 50. Look how many isotopes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 stable isotopes for tin. Has to have 50 protons, so it's got that magic number of 50. So these are trends. I find this fascinating. I'm hoping somebody else does here. See what else we have for your enjoyment here. We've got star charts, star charts, star charts. All we have are star charts. Okay, we will go to above, beyond 10. We're wasting time here, and I'm probably not going to edit this, so it's going to all be on there. Where's the chart above 10? 10, not 10. 9. Ribose. Standard model. Chart. Calcium.